Hi, I am Dr. Chandrakant Bonde. Today, we will discuss the structure of nucleosides and nucleotides, structure of nucleic acids, flavons and isoflavons, coumarins and porphyrins. This lecture divided into 5 modules as Module 1 contains structure of nucleosides and nucleotides along with nucleic acid. Module 2 contains structure of nucleic acid. Module 3 contains chemistry of flavons and isoflavons. Module 4 contains chemistry of coumarin and Module 5 contains chemistry of porphyrins. Let us start with the introduction of nucleoside and nucleotides. First, we will see the structure of nucleosides and nucleotides, that is DNA and RNA. DNA is deoxyribonucleic acid and RNA is ribonucleic acid, which are the polymers of nucleotides linked in a chain through a phosphodiester bond. In biological system, they serve as the information carrying molecules, or in the case of some RNA molecules, they act as a catalyst. This brief review will focus on aspect of structure of particular importance in manipulating DNA. Bases, nucleosides and nucleotides. We will see one by one. Nucleotides are the building block of all nucleic acids. Nucleotides have a distinctive structure composed of 3 components covalently bound together. A nitrogen containing base, either pyrimidine or purine, a 5 carbon sugar ribose or deoxyribose and a phosphate group. The combination of a base and a sugar is called a nucleoside. Nucleotides also exist in activated forms containing 2 or 3 phosphates called nucleotide diphosphates or triphosphate. If the sugar in the nucleotide is deoxyribose, the nucleotide is called deoxynucleotide, and if the sugar is ribose, the term ribonucleotide is used. There are 5 common bases and 4 are generally represented in either DNA or RNA. Those base pair and their corresponding nucleosides are described in this table which is shown on your screen. Another useful way to categorize nucleotide bases is a purine, that is A and G, versus pyrimidine C, T and U. Although committing this to a memory is often difficult, the importance is that in double-stranded nucleic acid, base pairs are always formed between a purine and pyrimidine. Now we will see the structures of nucleic acid. DNA and RNA are synthesized in a cells by DNA polymerases and RNA polymerases. Short fragments of nucleic acids are also commonly produced without enzymes by oligonucleotide synthesizers. In all cases, the process involves forming phosphodiester bond between the 3' carbon of one nucleotide and 5' carbon of another nucleotide. This leads to formation of so-called sugar phosphate backbone, from which the bases project. A key feature of all nucleic acid is that they have 2 distinctive ends. One is 5' and one is 3' ends. This terminology referred to 5' and 3' carbon on the sugar. For both DNA and RNA, the 5' end bears a phosphate and 3' end bears a hydroxyl group. Another important concept in nucleic acid structure is that DNA and RNA polymerases add nucleotides to 3' end of previously incorporated base. Another way to put this in is that nucleic acids are synthesized in 5' to 3' direction. Let us see the base pairing and double-stranded nucleic acid. Most DNA exists in the famous form of double helix, in which 2 linear strands of DNA were wound around one another. The major force promoting formation of this helix is complementary base pairing. A is forming hydrogen bond with T or U in RNA and G is forming a hydrogen bond with C. If we mix two ATGCs together, the following duplex will form. Examine this figure and note two very important features. The two strands of DNA are arranged antiparallel to one another. Viewed from left to right, the top strand is aligned 5' to 3', while the bottom strand is aligned from 3' to 5'. This is always the case for duplex nucleic acid. GC base pairs have 3 hydrogen bonds, whereas AT base pair have 2 hydrogen bonds. One consequence of this disparity is that it takes more energy to disrupt GC-rich DNA than AT-rich DNA. The figure fails to impart any appreciation of the three-dimensional structure of DNA. This deficiency can be rectified to some extent by viewing and manipulating the three-dimensional model of duplex DNA. Now, what about the double-stranded RNA? RNAs are usually single-stranded, but many RNA molecules have secondary structure in which intramolecular loops are formed by complementary base pairing. A simple example of this is shown in the figure on the screen, and much more extensive and complex examples are also known. Base pairing in RNA follows exactly the same principle as with DNA. The two regions involved in duplex formations are antiparallel to one another, and the base pairs that form are AU and GC. Okay, what about RNA-DNA hybrids? Can they form? The answer is yes. Complementary sequences of RNA and DNA readily anneal with one another to form duplexes. In fact, RNA-DNA hybrids are more stable than corresponding DNA-DNA and RNA-RNA duplexes. Now we will see the chemistry of flavons and isoflavons. Okay, I think you will got the insight about the nucleoside and nucleotide. Let us move to a chemistry of three important class of the compound, that is flavons, coumarins and porphyrins. Flavonoids are low molecular weight polyphenolic phytochemicals derived from secondary metabolism of the plants and play a very important role in various biological processes. They exhibit diverse types of properties that are beneficial for human health while interacting with number of cellular targets involved in critical cell signaling pathway in the body. Flavonoids can be classified into various classes like flavonols, the example is quercetin, camphorol, myricetin and fiestin. Next one is flavones, the example is luteolin and epigenin. Next is flavonones, the example is hesperidin and naringenin. Flavonoid glycosides are also there, the example is astragalin and rutin. Flavonolignan, the example is silibinin. Flavans, the example is catechin and epicatechin. Isoflavones, the example is genistein and diazepin. Anthocyanidins, the example is cyanidin, delphinidin. Orones, the example is leptosidin and aureosidin. Leucoanthocyanidins, the example is teracidinin. Neoflavonoids, the example is coutarigenin and dalbergin, and last but not the least, that is chalcone. All classes of flavonoids exhibit variety of biological activities, but among them the flavones have been considerably explored. Various natural semisynthetic and synthetic derivatives of flavones have been synthesized and evaluated for several therapeutic purposes. Flavones is a class of flavonoids based on the backbone of 2-phenylchromine 4,1, 2-phenyl-1-benzopyran 4,1. The molecular formula of flavone molecule is C15H10O2. It has 3 rings. The skeleton contains C6, C3, C6 and the ring are referred to as A, C and B rings respectively. Flavones have three functional groups including hydroxy, carbonyl and conjugated double bond. Consequently, they give typical reactions of all three functional groups. Flavones are colorless to yellow crystalline substances soluble in water and ethanol. They give yellow color solution when dissolved in alkali. Flavones are moderate to strong oxygen bases and are soluble in acids due to the formation of oxonium salts having pK values ranging from 0.8 to 2.45. Flavones have a planar structure with its COC bond angle, that is 120.9 degree. Its bond length between CO is 1.376 angstrom and dihedral angle is around 179.2 degree. The synonym of flavone are 2-phenyl 4H chromine 4-1 or 2-phenyl 1-benzopyran 4-1. Flavones can react in several ways including reduction reactions, degradation in the presence of base, oxidation, rearrangement, substitution, addition, condensation reactions with organometallic reagents. Several synthetic methods have been developed and modified to get products of high purity and of the desired quality. Flavones can be synthesized by various synthetic schemes like Glycosides condensation, Becker-Venkatraman rearrangement, ionic liquid promoted synthesis, Allen-Robinson-Vlesky-Bach reaction, Witting reaction, Fries rearrangement and modified Schouten-Baumann reaction. Nowadays, most of the flavones are synthesized based on Becker-Venkatraman method. It involves the conversion of orthohydroxyacetophenone into phenolic ester, which undergoes an intramolecular Claisen condensation in the presence of a base to form beta diketone, which is cyclized to flavone by an acid catalyzed cyclodehydration. Traditionally, flavones were synthesized with Becker-Venkatraman rearrangement, but these reactions undergo the use of strong bases, acids and long reaction time, as well as they are giving low yield. The simplistic and alternative synthesis of medicinally important flavones in which 2-hydroxy chalcones resulting from condensation between acetophenones and salicylate undergoes oxidative cyclization on heating in presence of catalytic iodine and generating diversified flavone under solvent-free environmental friendly conditions. Now, we will see the chemistry of coumarins. Coumarins are the benzopyran 2-ones which constitute an important class of naturally occurring compounds. They are widely used in perfume, cosmetic, agrochemical, pharmaceutical industries, etc. Several coumarins derivatives have been synthesized, prepared and reported to possess cardiovascular, aging, antibacterial and phosphosensitive properties. The chemistry of coumarin has received much attention and is used by chemists to develop several useful products. The chemistry of coumarins has centered on performing reactions activated C3-4 double bond of a beta unsaturated lactone. Based on this chemistry, heterocyclic systems have been built. Coumarins with the desired aromatic substitution were built by synthetic starting from appropriate starting material and by electrophilic or nucleophilic substitution. Now, we will say about 3,4 fuse coumarin. Reactions of 3-acetyl coumarin with phenacetyl halide in presence of sodium ethoxide gives 3,4-phenacylidene 3-acetyl-coumarin due to insertion of methylene across the C3-4 double bond. The product is 3,4-dihydrocoumarin derivative. Now, we will see the cycloaddition reactions. The photodimers of coumarin have been known from last 60 years. These have been of the interest as furocoumarin and are known to react with the skin in presence of light. They have been used for the treatment of skin depigmentation. Photochemical reaction across the double bond of coumarin is reported to give you 4 and 6 member 3,4-dihydrocoumarin dimers, 3 and 4 respectively. Due to 2+2 and 2+4 cycloaddition, reactions are also shown in the diagram. Naturally occurring coumarin, aflatoxin, that is B1, B2, G1, G2, M1, M2, 1 form a group of acutely toxic and extremely carcinogenic hepatotoxic metabolites produced by some strains of Aspergillus flavus. Aflatoxin B1 has been synthesized from the starting material 5-benzyl-oxy 4-methyl-7-methoxycoumarin via corresponding 4-formyl derivative. One of the yellow pigment isolated from the scent gland of the beaver has been identified as urethane A3 and urethane B4. Alternariol is the first 3,4-benzocoumarin antibacterial agent of fungal origin isolated from Alternaria tenace. Benzocoumarins, atomeriol and atomerinol isolated from bulbs constitute the flavored component of the shilajit. Furocoumarin, glapelol and coumestan, namely coumesterol, have been isolated also. The accumulation of compounds known as phyloalexin and the concomitant shift in the metabolism are believed to be the mechanism for disease resistance in the plant. Lastly, I am going to introduce a beautiful molecule having the name of jewels, a porphyrin. Has a purple color, but the color changes depending on the number of pyrrole units and the number of carbon atoms connecting the pyrrole units. These molecules are therefore named after the jewel stone of corresponding color. Now we will see the chemistry of porphyrin. As shown in the diagram, a porphyrin is a rigid, square planar molecule made up of 4 pyrrole connecting to form a larger ring. The molecule is stabilized by the aromatic character which extends over its entire structure. A porphyrin has 4 of its nitrogen atoms facing the center, which can capture a metal ion to form a very stable organometallic complex. It turns out that this property of the molecule is closely linked with the way it is used in the living system. When forming a complex, many metal ions accept 6 coordinating ligands to assume an octahedral configuration. The nitrogen atoms of a porphyrin occupy the 4 sides of the square plane of octahedron, leaving 2 empty sides on the top and the bottom. These 2 sides are then filled by axial ligands which are known to react in a special way. By using them, biological systems carry out a wide range of chemical reactions. Let us see oxygen as a carrier. If we will see at the hemoglobin, a carrier of oxygen molecules in the blood as the first representative example. Hemoglobin has a structure in which porphyrin part called heme is connected to a protein. Positioned at the center of this heme is an iron atom and a molecule of oxygen attaches to it as an axial ligand. An oxygen molecule is not a strong metal binding capability naturally, so it is usually doesn't form a stable complex with metal ions, but porphyrin makes it happen, showing its unique ability. Hemoglobins are designed to capture oxygen molecules actively in the places where there is an abundance of oxygen and to release them when there is a shortage. A liter of human blood is said to have the capacity of carrying the same amount of oxygen contained in 1 liter of air, which tells you about the efficiency of the chemistry. Chlorophylls and vitamins like animals, plants also rely on an important compound with the porphyrin skeleton. The molecule found in the plants is chlorophyll, which is responsible for green color pigment normally seen in the leaves. Vitamin B12 also contains a similar structure called choline, and it is an essential compound in the synthesis of nucleic acids. At the core of the choline skeleton sits a cobalt atom, a relatively rare entry for biological molecule. As you see, the overall structure of vitamin B12 is exceptionally complicated. The chemical synthesis has been considered impossible, but it was accomplished by collaboration between two extraordinary chemists, that is Professor R.B. Woodward and Professor Albert S.N. Moser, with their report published in 1973. If you will see the choline structure, the left side half of the choline structure was made up by Woodward in the United States and the right side was done by S.N. Moser in Switzerland. The big project over the Atlantic Ocean was completed by joining the two parts together at the end. It was an incredible achievement that took over hundreds researchers in the two groups combined, more than 90 synthetic steps in total and 12 years of effort. There is no report of second total synthesis of this compound even today, when synthetic methods are so much more sophisticated. The synthesis is considered as a landmark achievement in the history of organic synthesis. Woodward also developed a theory now known as Woodward-Hofmann rules by analyzing stereochemical observations made during a key step in vitamin B12 synthesis. Professor Hofmann, a collaborator of Woodward who did these theoretical calculations, received a Nobel Prize in Chemistry in 1981. It's amazing that a Nobel Prize was born as a side product, but this may be a good example where a great discovery was made by challenging a difficult research. With all these information, here we come to the end of today's lecture. Do keep in mind what we discussed today. It's time for you all to do some self-study. This is Chandrakant Bonde signing off. If you want to learn more and enhance your knowledge, you may log on to our website for quizzes, FAQs, LORs, that is www.cec.nic.in. Till then,